Hello everyone. So today I'm going to explain the composite beams, and we basically are going to calculate the bending stresses and bending strains for the composite beam. So let me first define what is composite beam. So composite beam, they are basically beams that is made of two or more materials. For example, we use this in reinforced concrete, where concrete, for example, is very weak in tension and very strong in compression. So we put steel rebars in the concrete so that the steel rebars can support the tension and the concrete can support the compression. So we use this composite beam idea or concept in reinforced concrete, and also we can use it in timber. How can we strengthen the timber beam? So remember the bending formula that we concluded before, that is my over I, it was based on one material. So this equation will only work if we have a cross section that is made of only one material, fully concrete. So steel, which is here, is a cross section that has steel and concrete. This bending formula cannot work because basically in the bending stress formula we do have the moment of inertia, which, if you remember, that we used the moment of inertia in our derivation from before, that this was based on if we have one material in the cross section. Same as the centroid. So y was the distance from the centroid to the point where you want to calculate the stress at. And if you want this, if you remember how we drive the centroid, we canceled, like in the equation in that lecture. If you don't remember, go back to that lecture. We canceled all the material together, and when we cancel all the material together, that means we have one material, or we have a cross section that's made of one material. So what should we do? So what we're going to do now is, if we have a cross section that's made, for example, of two materials like wood and steel, we want to come up with a way that we can convert either of the two materials to one material, so that we can end up having one cross section. So we can do this. We can convert the steel to wood, or we can convert the wood to steel. So what I want to come up with a cross section. So I'm going to copy this. I'm going to keep the height. So what I want to do, I want to come up with for example, let's decide I want to convert the steel to wood. So this steel will be converted to wood. This steel will be converted to wood, so that I will have a cross section made of wood, wood, wood. But the thing is, I can't convert the steel to wood randomly. And here comes this method, which is transform section method, which is I want to switch, or I want to convert the steel to wood, or in different words, what is the amount of a wood that I can put here that can replace a steel, and it also can get me the same behavior as the steel. So you might agree with me that steel is stiffer than the wood. So what I'm looking for here, I'm looking for the amount of wood that can carry an equivalent load that this steel was carrying. So you agree with me that now I have to increase the area of that part and that part, because now I'm converting these two parts from steel to wood. So now this is wood, and this one is wood now. Okay? So now I increase the cross section of the wood, or I increase the dimension of the wood. I widen the wood so that I am putting the amount of the wood that can carry an equivalent load that this steel was carrying. And because steel is stiffer than the wood, then not the same dimension of wood I will replace it with steel. No, I will increase the dimension of the wood so that it can support an equivalent loads that the steel was supposed to carry. This method, we call it transform section method. And if you notice, I only increased, or I only widened the wood. I only increased the width of the wood. I didn't play with the thickness. and I maintain the same height of the resultant transformed beam. And I will tell you that in a couple of slides that will come later. But now, let's agree on this. This method is called transform section method, where I convert either of the material, and let's fix this. I will convert the strong material, which is steel, to wood. So now, from now on, any section that you will have, always look for the strong material and convert it to the weak material. You can do the opposite, but let's fix it that way. Let's convert the strong material to a weak material. Okay? So what we did now, we converted the original section, which was made originally of from two materials, which is steel, wood, steel, to a cross section that is made of one material, which is wood. And we did that by increasing the dimension of the wood. But the thing is, how much are we going to increase that dimension? And here comes the idea of what is the amount of wood that can we add that can be equivalent to the steel? And here comes the concept of the equivalent beam, or equivalent cross-section, which is basically tells you how can two different materials be equivalent. And think of it that way. If I do have a river, and I want to design or build a bridge that crosses that river, I have options. I can build that bridge with concrete, I can build that bridge with steel, I can build that bridge with timber or like wood. But the thing is, they will all serve the same function, which is having the car crossing the bridge, or like the people crossing that bridge. Of course, if I build it with concrete, I will have like a very big column dimensions and beam dimensions compared with if I build it with steel, because steel is stiffer. But at the end of the day, if I build it with either material, I need to serve the function of people like crossing the bridge safely or crossing the river safely. And by safe mean, the bridge shouldn't deflect much, whether it's made of steel, whether it's made of concrete or timber. And here's the idea. For two beams or for two materials to be equivalent, both of them need to have the same strain, so the same bending strain and radius of curvature. And if you remember, the radius of curvature was rho, and the strain, normal strain, was epsilon. Okay? And here's the thing. So if I have a beam, it was originally like this, and when I applied a bending moment, it bent that way. And here's the radius of curvature. So the radius of curvature is the radius from the neutral axis to the center of the curvature. So I need the two beam to have the same rho and to have also the same bending strain. The second condition is I need both beams, which is made of different materials, to have the same bending strain distribution. Let me write it down. Bending strain distribution. And I'll explain that in a moment. But if you remember, the equation for the strain was equal to epsilon is equal to y over rho. But if the strain of the original cross-section, which is, for example, if I'm now explaining the concept of equivalent beam, which is having two material equivalent to each other. So for example, the epsilon of steel, of that steel beam, I want to remove the steel and put the wood. So, and here is the epsilon of the wood. I want the epsilon to be the same, and epsilon gonna be y over rho. So if you remember, I just said now, for two beams to be equivalent, that's made of different material, they need to have the same strain, which is the deformation, and the same curvature, radius of curvature. So they're gonna be the same. So since the two beams gonna have the same radius of curvature and same strain, so the y should be the same. And y here is like the vertical coordinates, and if you remember, y is the distance from the centroid where you want to calculate the stress at. So if epsilon gonna be the same for the two material, and rho gonna be the same, so y should be the same, which is the vertical distance. That's why I told you earlier that when I convert two sections to each other, like when I convert steel to wood, I only change the width. I don't change the height, so that the epsilon for the whole beam not gonna change, because the y, I want the y for the original beam to be equal to the y for the translated or transformed beam. So here's the condition. The second condition is the bending strain distribution. So I want the aluminum, I want, for example, steel or aluminum. I just mentioned earlier it's a steel, but let me write it here as aluminum, as steel, sorry. I want both of them to have the same strain, bending strain distribution. So due to bending moment, for example, if this is a cross section that has a bending moment like this, I want the strain to have the same bending strain distribution. Here is E, negative, positive, and here is E. So I want the original material, which is steel, and the equivalent for the steel, which is made of wood. I want both of them to have the same bending strain distribution. So having the same eta, so if eta, for example, is 0.1, and down here 0.1, so I need the bending strain distribution for the wood also to be the same. And notice here, the height are the same. Therefore, eta is like epsilon gonna be the same. And y, which is epsilon, is equal to y over rho. Y is the distance from the centroid to the point where we want, for example, to calculate the strain at now. So if I have a y at this point, which is h over 2, this h over 2 needs to be like this so that I will get the same strain. That's why we fix the height and we just change the width. Okay? So let me name this diagram, which is bending strain distribution, and we practiced on that last lecture. And let us practice the concept of the equivalent beam, which is, for example, now I gave you an aluminum beam which has a cross section of 15 times 40 millimeters and has a modulus elasticity of 70 gigapascal, bending moment of 140, and it's placed that way, so the arrow looks up, which means the upper side is compression, the lower side is tension. And I'm asking you, find the wooden beam that is equivalent to that aluminum beam. So if we want to have two materials to be equivalent to each other, if you remember from the previous slide, they need to have the same radius of curvature and the same bending strain, and thus it should have the same y, which is the same height. The second condition is to have the bending strain distribution. So let's start first by finding what is the strain for this cross section and also the radius of curvature, and we will design the wooden section that's equivalent to this based on those two terms. So let me first find the epsilon for the aluminum, and it is y over rho. Okay? I don't know what the rho is, and I will be calculating the strain at the ends, at A, and let me name this point at the bottom here, B. Because if you notice, epsilon is directly proportional to y, and from the previous lecture, we had the bending strain at the far ends of the cross section will have the maximum strain. That's why I'm interested in them. And of course, at the neutral axis, I'm expecting to have a zero strain because also y gonna be equal to 0. But the problem here, I don't know what is rho gonna be. So let's find rho. And if you remember, rho for aluminum, the rho equation was equal to E, which is modulus of elasticity, I sub x, m sub x. And the E, which is modulus of elasticity, it's 70 gigapascal, and gigapascal is kilonewton millimeter square. I'm going to multiply this by 1,000 to convert the kilonewton to newton. So that's the first term. And then modulus of moment of inertia for this cross section, Ix, parallel perpendicular cube over 12. So parallel to x, which is 15 times 40 cube over 12. So I'm going to write 15 times 40 cube over 12 over m sub x. And m sub x here is given. It is 140 Newton meter. And I'm going to multiply by 1,000 to convert this meter to millimeter. Okay? I'm gonna end up with a rho equal to 40,000 millimeter. Okay? So now I can calculate the epsilon at A, and it's gonna be also equal to B. And the epsilon gonna be y, which is the distance from the centroid to the point where we're going to calculate the stress at, which is A, which is going to be 20 now. And also at B, it's going to be 20. So I will say 20 millimeter over 40,000 millimeter. I'm going to get 0.0005. Okay? So if I want to draw the bending strain distribution now for this beam, it's going to be at the top compression, and at the bottom I'm having a tension. Okay, and the strain at the top 0.005, and the strain at the bottom equals 0.005. So now I found the strain, so the epsilon for that cross section or for that beam, and I found the radius of curvature. So now if I want to find an equivalent cross section made of any material, I need to have that cross section has the same rho and the same epsilon, and using them I can find the moment of inertia, and using that moment of inertia I can get the new dimensions for the equivalent section. But now I just ask you that I want the equivalent cross section be made of wood that has the E equal to 10 gigapascal, and also the M, which is the same bending moment, 140. So same bending moment, but different E, because of course it's a different wood. So wood has different modulus of elasticity. So what I'm going to do now, I want to have this cross section that will have the same height, which is 40, as we agreed. We're gonna fix the height, but we're gonna change the width, which is B. I want to find what is the dimension for B. And at the beginning, before solving it, I know that the B is gonna be larger than the original section. So I'm gonna widen this wood, because wood has less modulus of elasticity. So I'm gonna say, okay, I wanted, because the epsilon for aluminum was 0.0005, and the rho for aluminum was equal to 40,000 millimeter, right? I want them to be equal to the wood as well. So I'm gonna say now that the epsilon for wood is equal to epsilon for aluminum, same as rho for wood is equal to rho for aluminum. So now the rho of wood, which is the radius of curvature of wood, is equal to 40,000, is equal to the equation, which is EI over M. So the E is 10 gigapascal multiplied by 1,000 to convert the kilonewton to Newton. So now I have a Newton millimeter square, and I want to find the new inertia for that new cross section, or the transformed cross section, over the moment, which is the same moment, 140 multiplied by 1,000 to convert the meter in the Newton meter in the moment to Newton millimeter. So the moment of inertia is equal to 560,000 millimeter power 4. And Ix, which is equal to BH cube over 12, and I is equal 560,000, is equal to B, which is the unknown now, H, which is the height, it is known, which is 40 power 3, and then over 12. And I found out that B is equal to 105 millimeter. So to have an equivalent cross section, to have an equivalent wooden cross section for the 15 times millimeter aluminum, I need to have 105 width millimeter times 40 millimeter of wood. So this section is equivalent to 15 times 40 of the aluminum. Okay? So let's find how much we change the width of the beam by. And if I say the B wood over B of the aluminum, which is 105 over 15, I'm getting 7. So the ratio of the width of the wood to the width of the aluminum is 7. So the aluminum, of course, is 7 times the width of the wood. Okay? And of course, because of the aluminum is stiffer than the wood. But here comes another question. Okay, now we came up with a cross section that will have the same radius of curvature, same strain, and same bending strain distribution, because again, I didn't draw this. If I want to draw the E, so the E here, we set it at the beginning equal 0.005, so it's going to be the same as what we had before. So negative, positive 0.005. Okay? Which is basically 0.305, which is equal to, strain is equal to Y, which is 20 over rho, over 40,000. You're going to get 0.005. We didn't change anything. So now we came up with a cross-section that will have the same radius of curvature, same strain, and same bending strain distribution. Okay? But here comes the question. Okay, we changed the cross-section as obviously what you see here, but now, will these two equivalent beams will have the same stresses? Let's find out. So let me calculate, for example, for the aluminum, let me calculate the stress at A. So stress at A is equal to my over I, m sub x, I sub x, and m is 140 multiplied by 1,000 to convert it from Newton meter to Newton millimeter, multiplied by 20 because y is distance from the centroid to the point where we want to calculate the stress at. So this is 20 over 15 times 40 cube over 12. And I got 35 megapascal. If I do the same with the transformed wood or the equivalent wood section, I'm going to use the same equation because I have the same moment. I have the same y, which is 20, but I don't have the same inertia. So the inertia is 105 40 cube over 12. And I'm getting a stress is equal to 5 megapascal. So a conclusion here is that the equivalent beam do not necessarily have the same bending stresses. And if you notice, both of them has a bending strain of 0.005, 0.0005, which is 3 ohs 5. So they have the same strain at this bending stress. So at the stress equal to 35 megapascal for aluminum, the strain at A was equal to 0.0005. Same as here, the strain as A for the wood was equal to 0.005. So here's the conclusion here also, which is it takes high stress, which is 35 megapascal, to have a strain is equal to 0.0005, and for wood it takes low stress, which is 5 megapascal, to get this strain, which tells you the aluminum is of course stiffer. But let's find the ratio between them. So the stress of aluminum over the stress of wood, which is 35 over 5, I got 7, which is the same ratio that I had from the width. But the thing is, where does this 7 come from? So this 7, we're going to discuss it in the next slide. But let me talk about something. How can, at the same strain, I'm getting like different stresses? Of course, because of what we discussed in lecture 2, which is the stress-strain diagram. So of course, steel is stiffer than the wood. So I'm going to have a stress-strain diagram looking something like this, which is close to 90 degrees, which has like a very big slope. But for the wood, I'm going to have something like this. Okay? And for the same strain, which is 0.305, for the same strain, if I went up and hit the graph, I'm seeing that at the same strain, the wood, which is this is the wood and this is the aluminum, I'm having stress that is different than that stress. So the difference here in the stresses, although have the same strain, comes because of the modulus of elasticity and like the stiffness of the material. One of them is stiffer than the other. So now let's find where this 7 came from. So we agreed from the beginning that the epsilon for aluminum is equal to epsilon for wood, so that both of them are equivalent. Okay? And the bending strain or the normal strain is equal to a stress over modulus of elasticity. That's for the aluminum side, and then I do have for the wood side stress over the modulus of elasticity of the wood. So let me put it in let me put the E's in one side, which is modulus of elasticity in one side, and the stresses in the other side. So I'm gonna move the aluminum here, the E aluminum, which is modulus of elasticity aluminum here. I'm gonna take a wood down. So I'm having E for aluminum, E sub wood, equal to a stress of aluminum, a stress of the wood. So if you remember, the E modulus of elasticity of aluminum was equal to 70, and the epsilon or the modulus of elasticity of wood was equal to 10, which is equal to 7, which is same as the ratio of the stresses of the aluminum over the stresses of the wood, which was 35/5. So now I know the 7, where the 7 came from. So the 7 is the ratio of modulus of elasticity of aluminum over the wood. And this term, or this ratio, we call it modular ratio. So modular ratio is E of a material over the, for example, aluminum over wood, and we call the ratio N, and this is modular ratio. In the book, they put the modular ratio as like E wood over E aluminum, and sometimes E aluminum over E wood. In different words, you can have an N, E modulus of elasticity of a strong material over modulus of elasticity of a weak material, or the opposite, the modulus of elasticity of a weak material over the modulus of elasticity of strong material. But for this class, let's fix it that way. I want to fix it that E strong over E weak equal to N, and therefore it will always be greater than 1. So let's fix it that way and work it that way. If you did the opposite, it's not wrong, it's correct. But like let's fix it that way so that we are consistent in our solution. Okay? So what should we do in like when we have a problem that asks us calculate the bending stress, for example, when we do have two materials? So the first step is calculate the modular ratio, which is N E strong over E weak. And then after getting the N, I want you to convert the strong material to a weak material and calculate the centroid and I transform. So let me go over those steps while solving this problem. So I do have an example where I do have a cantilever beam with a distributed load of 100 pounds per foot. And then the cross section, it is wood and I think aluminum. Wood and aluminum, and the modulus of elasticity are given. Okay, first step, we calculate the bending moment diagram. So I didn't spend time here because we practiced that before. So the bending moment for this cantilever is 5,000 pound per pound foot. So now let's start with the steps. I want to calculate the modular ratio, which is N E strong, which is the strong here is aluminum, over E weak, which is the wood. Now I do have 10,200 over 1,700, and I'm getting 6 as a modular ratio. Of course, after this, the steps I need to convert the aluminum to wood, because I can't calculate the centroid and moment of inertia for this beam that has both cross section. But let's put the axis of bending first. So the axis of bending, due to this cantilever, they gonna bend around Z. So if you applied a load like this, it's gonna bend around Z, and Z is here horizontal, okay? And the axis of bending now is horizontal. So it's important to identify the axis of bending, because that's where we're gonna calculate the moment of inertia about. So to summarize, I will convert the aluminum to wood. I'm converting always the strong material to a weak material. So I copied it the same, because I want to preserve the height. I don't want to change the height of the cross section. I'm only gonna change the width of the cross section. And the width of cross section is, I'm gonna multiply the width of the cross section by modular ratio, which is what we did before. So if you remember, for the two beams to be equivalent, B wood was equal to, if I want to write it down, B wood was equal to 7 times B aluminum. Okay? So B wood is, we widen the wood by factor of 7 of the original width of the aluminum. And that's what I'm going to do now. So let me highlight this. I'm going to multiply the width of the aluminum by 6, which is the factor. And when I multiply 6 times 3, I'm getting 18. So I'm going to widen the aluminum by multiplying by 6, so I'm having 18. So let me organize this. 3 inch by 6, which is the modular ratio, 18 inch. So here's the new cross section, and I'm going to erase this. I'm going to write wood. So now I have a T section made of one material, so I can calculate the centroid and calculate the moment of inertia. Around what? Around the axis of bending, which is Z. Okay? It's important to identify the axis of bending, because if the loading was different and the axis of bending was Y, for example, that's going to change how you're going to calculate the moment of inertia. So it's important to find the axis of bending, because that's where you're going to calculate the moment of inertia about. So I'm going to give the answers here for the centroid and the moment of inertia, and I'm gonna I'm gonna have it in the PDF in like details how we're gonna do this, because I explained, we went through this before, calculating the moment of inertia of the T section. So I don't want to spend time here, because we did that before. So the Y bar gonna be equal to 4.651 inches, which is this distance. Okay, and the moment of inertia for this transformed section, we're gonna call it I sub transformed. Okay, and this is Z, around Z, of course. And this is gonna be equal to 192.504 inch power 4. So now I do have the centroid and I do have the moment of inertia. So now let's find the stresses. And if you remember from the stresses the lecture, we said that we only calculate the stress at the top and the bottom. But the thing is, in composite beams, we're gonna add 2 more points. So at the point where the interface between the two material, so it's important to draw the original material here, the original beam here, and right next to it the transport, so you know where is the interface. So at the interface, I'm gonna calculate the stresses. So let me point out the stresses here. So I want to calculate the stress here. I'm gonna call it 1, and of course here, and let me call it 4. Or let me call it 3. Okay? And here, which is here now, I'm gonna call it 2. And here's 2. But what is the difference between them? The first two here, so the two points here, which is, of course, it's 1 point. One of them, it's gonna be just above the interface, like just above, and one of them just below. So if the first one here, that 2, is just above, so we are in the aluminum. And here is done, for example, point number 1, we are in the aluminum region, or the aluminum part. And the 2 here, which is just below, we are now in the wood part. That's why it's important to have the two cross-section right next to each other to know where is, for example, point 1 here, so point 1 in the aluminum part, point 3 here in the wooden part. Okay? And calculate the stresses like what we did before. So let me start with stress 1 for the aluminum. I'm going to say stress 1 aluminum is equal to my over I transformed. But here's the thing. We transformed the aluminum to the wood. So we increased the area of that wood. But always remember, we did this because it's a maneuver. That's not the real section. That's not the T section is not the real section. The real section is this section. And of course, the real section doesn't have all this area. And if you remember, from practicing the concept, we found that when we found the equivalent wooden section, there was a difference by a factor of 7. So we got a very low stresses here, because of course we increased the area. When we increase the area, we have a very big I, which is the moment of inertia, and therefore we had low stresses. But to correct this, we found that the ratio here was 7, which is basically the stresses of the aluminum, which is the original material, is equal to 7 times the stress of wood. And let me highlight this. And this is what we're going to do also. So we're going to find for all the transformed wooden part, which is 1Al and 2Al, my over it, and then we're going to modify this stress by n to convert it now from wood to go back to the aluminum. Okay? I hope it's clear. So for 1Al, I'm going to multiply by n. And also that's going to be the same for 2Al, which is my over I transformed and multiplied by n. So what was m? So the moment here was down, so which tells you the lower side of the beam. So if I have a beam like this, so this is the beam, the moment turned to be down, and the moment tells you where the compression is. So the lower part of the beam here is in compression, okay? And if the lower part is in compression, we label this in 2D by having a moment a line that has an arrow looking down. And we went through this before. So here is the moment, and the arrow here looks, the reason why we put the arrow down, because the arrow points toward the compression side. So if I draw the arrow down, means the lower part of the cross section here feels compression, and the upper part feels tension. So now it's easy for me to identify, because the stress equation is plus or minus my over I. So now when I know, okay, point 1 here, which is here, it is in the positive region, so I'm going to put plus. So plus the moment, which is 5,000 pound-foot. Let me write it down here. So I'm going to write 5,000 pound-foot, and I'm going to multiply this by 12 to convert the pound-foot to pound-inch, and then multiply by y, which is the distance from the centroid to point 1, to the point where we want to calculate the stress at. Popular mistake or common mistake, students used to calculate the stresses at the center of, for example, this member. No, we calculate the stresses at the edge. So y here is going to be equal to 3.599 inches over IT, which is what we calculated, which is 192.504. don't forget to multiply this by n, which is 6. What I'm getting is 6.73 KSI, okay? And I didn't write it here, but I divided everything by 1,000 to convert the pound to kilopound. So now that's why I have the KSI, okay? Same thing gonna be here, so I'm basically gonna copy this equation because all the stress equation for all the points within the beam gonna have the same moment, the same I, which is the moment of inertia. What's gonna change is y and whether or not to multiply by n. So I'm gonna change now for the 2L, I'm gonna change the y, and it's gonna be this distance, which is 3.349, and the equation gonna be, sorry, the answer here gonna be 6.262 KSI, okay? So let's move and continue to stress for 2 wood. And again, I'm gonna copy everything. I'm gonna copy this. I do have the same moment. I do have the same I. And the y here is gonna be the same. But now what's the difference is I'm not gonna multiply by 6. So the answer here gonna be, so point stress at 2 aluminum is same as 2 wood in everything in the equation, except that for 2 wood we don't multiply by n because the cross section was originally wood. We didn't transform this part, we only transformed that part. So for all the parts that we transformed, we multiply by n. For the parts we didn't transform, we leave the equation. We don't need to modify anything in the equation, okay? And again, the reason why the I transformed in all points here, because I transformed is the moment of inertia, and it covers, or like it take into account the behavior or the behavior of the aluminum, okay? And I'm getting here 1.044 KSI. And finally, the last point, which is stress 3 wood, I'm gonna copy everything here. I'm gonna put it down. And you can program that in your calculator to have the same M and I. But now in this part, I'm putting negative because 0.3 here falls in the negative region, which is the compression side due to the bending moment. What I'm going to change? I'm going to change the y because the distance from the centroid to 0.3 is 4.651. And I'm not going to multiply by m because this was originally wood. So 4.651, and the value is negative 1.449 KSI. Okay, now let's draw the bending stress distribution. So since we have the moment vertical, so I'm gonna draw the reference line here that I'm gonna draw the stress about is gonna be vertical as well. So if the moment is vertical, so now the bending stress distribution, the reference line here, is gonna be vertical. So here is called bending stress distribution, and I'm gonna draw the line which indicates where I want to calculate the stress at. For example, I draw this line because that's at 0.1. I'm gonna draw at 0.2, and of course I have the centroid, and I don't usually draw the centroid for the bending stress, but now the neutral axis aligns with the centroid, because if you remember, if I only have a cross section that has only bending moment and no axial force, the neutral axis aligns or coincides with the centroid. So now this line, the red line, is the neutral axis. So this is the neutral axis where the stress is equal to 0. And let me continue these gray lines, and finally at the end here. Okay, so at the top, at 0.1L, I do have 6.73. And again, I don't care whether you draw it right to the left, as long as within the triangle, you are telling me it is positive or negative. So I do have 6.73 KSI. 0.2L, it is 6.2. So it's going to be less here, 6.262. So I'm going to go down like this. And for 0.2 also, I do have the 2 woods, which equal to 1.44. So you're going to see a drop here, which is 1.044, and then blindly take this line to 0. And then extend this line. So I'm going to extend it. And if I draw to scale, it's gonna be extended. And I tell you now in a moment why. And at the end, I'm going to write 1.44 KSI. And here is negative, here is positive. Since the bending stress equation is my over I, for every material, you're going to notice that it's a straight line. So because I have aluminum here, it's going to be a straight line. Because I have a wood here, that's why you see a straight line here. And the reason why you saw a drop here is because you have an interface or you have a change in the material. And the reason why the stress is dropped to a small value instead of dropping up, so it dropped down to 1.044, because we are going from aluminum, which is a stiff material, to a weak material, which is wood. That's why we went down. But if we have the opposite, which is if we had wood up and we had aluminum down, we will drop up, because at the interface here, we are moving from weak material to a strong material, so I will go up with a very high stress, then I will go to 0. Finally, I want to draw, or I want to calculate the strains. But here's the question. Let me resize this. So this is the stress equations. The question will be here, will the bending strain gonna be a straight line, or it's gonna be a line, then it's gonna drop, and then so the question is it gonna be a straight line, or it's gonna follow the same shape as this, which is like you're gonna see the drop. Let me show you a video, which is a test experiment that happened by Professor Tim, and we can conclude that after this. So he has a reinforced concrete beam, and there is a steel rebars inside, which is here's the beam, and you have here like steel rebars, and we applied a force which will cause this beam to bend. So we applied 2-point loads here. Okay? I want you to notice how this beam bent. I'm gonna have it in I'm gonna speed it a little bit. Okay, so here it broke. But before it broke, look how it bent. So the steel didn't pop out here before it broke. So my point here is that the steel inside the beam, which is here, which is this cross section, the steel inside, the rebar inside, was bending along with the beam, which tells you that at the interface between the reinforced concrete and the steel, they have the same strain. Because if they have this different strain, you will see that the steel will pop out, which is, if I want to draw the strain at any point here, for example, at any point, okay, I'm going to have tension at the bottom and compression at the top. But at this point, which is the interface between the steel, the rebar, and the concrete, they have the same strain. You don't see any drops. Because if you would see drop, that means that the steel is deforming differently than the beam, and you would see like the steel is popping out. But as a part of having this beam working together, they need to have the same strain. Otherwise, they'll not be working together if they have different strain. That's why you should expect to have a strain here, to have a strain that is linear. Okay? And it's going to follow the same signs. But if you're not convinced, let's calculate the strain at all these points. And if you remember the equation for the strain, for example, at 1 AL is equal to stress over modulus of elasticity. So the stress here, I'm going to simply take this value, which is 6.73, divided over the modulus of elasticity of the aluminum, because 0.1 here was in the aluminum. And the aluminum was 10,200. Okay? So this is KSI, the bottom is KSI, and I'm getting 659 times 10 power negative 6. And I don't want to write 10 power negative 6, so 10 power negative 6 is micro, so I'm going to write micro strain. So now that's at the top. So 659 micro strain. Let's calculate it here. So strain 2AL, which I'm going to take the stress, which is 262 over 10,200. And you're going to find it is 614 microstrain. So at that point, it is 614. So now let's calculate it at 2 wood. You're going to have 1.044. But now we don't use the 10,200 because now we are in the wood region. So I'm going to use 1,700. So for 1,700, you're also going to find the strain is equal to 614. And at the same point here, you have a same strain. You don't see any drops. That's why from now on, for this type of problems, I want you to calculate the stress at the top and the bottom and just make a line between them, and that's all. And finally, the strain 3 wood is equal to negative 1.449 over 1,700, and you're going to find the strain is equal to negative 847 microstrain. And let's name this diagram because we have multiple diagrams here, so it's important just to differentiate between them. Now I have bending strain distribution. Okay? And that's all what I have, and I will see you soon. Thank you.